So in this video, I want to do a little bit of compare and contrast for two Galois groups, both degree 4, and I want to kind of work through these and use our understanding of algebra to sort of see where the structure of the Galois group comes from. We're really trying to focus on building some intuition here. So the first one I want to look at is x to the 4 minus 10x squared plus 1. So it's a degree 4 polynomial. We're going to look at this defined over Q. And so once we find a splitting field, we know that the Galois group that we're looking at is going to be order 4. And we know that there are two groups of order 4, right? The two choices for order 4 groups are, we have z mod 4z and z mod 2z times z mod 2z. And I want to figure out, using my knowledge of algebra, which of these correctly describes the symmetries that this object has. So when I see one of these quadrics in a quadric, if you will, I make a substitution, x equals y squared, get it down to here, and now I solve this with the quadratic formula, right? I'm trying to figure out what the root field of this thing looks like. So I got 10 plus or minus 100 minus 4 over 2, or 5 plus or minus, what is the square root of 96? I could take a 4 out of there and get the square root of 24. That could be simplified a pinch further down to 5 plus or minus 2 square root of 6. Okay, that gets us y. And then x must be the square root of that, right? It's the square root of 5 plus or minus 2 square root of 6. And actually, we had a fact from a homework problem, which was that f adjoin the square root of a plus b plus 2 the square root of ab, this whole big mess, is isomorphic to f square root of a square root of b. And so inspecting this, I can see that this is 2 plus 3 plus 2 square root of 2 times 3, right? It's of that form, which means that if I take q and I adjoin this x, it is actually exactly the same as adjoining square root of 2 and square root of 3 separately. Using so now with our field theory knowledge comes to save the day. And we know this field, right? We know it's Galois group, right? The Galois group of Q adjoin these two elements over Q. We saw it last video. It's Z mod 2 cross Z mod 2. With two independent automorphisms, right? You have we could call them sigma, which is the one that sends 1 to 1, square root of 2 to minus square root of 2, right? It's a permutation, if you will, of the roots. And then we have the permutation tau sending 1 to 1, square root of 3. This one gets, square root of 3 over here gets preserved. Square root of, let me try to write them in the same order so we don't get confused, right? This one preserves square root of 2 and flips square root of 3. And then, of course, you have the composition, right? Sigma tau, or tau sigma, which they have to commute because this group is order 4 and all groups of order 4 are abelian. So tau sigma equals sigma tau, just from the order. But in general, there's no reason why elements of Galois groups have to commute, and they oftentimes won't. And so one of the things that one can do when one is starting to work out the Galois group is take a look at the elements that you find, right? When you construct, you have maybe some partial information about the root field. You can say okay, well, what's the order of this element? And then you find another element. What's the order of that element, right? You know, from Lagrange's theorem, Lagrange tells you the order of a subgroup, including a cyclic subgroup generated by an element that you find, has to divide the order of the group. And in fact, you may know the order of the group because you may know the polynomial. So you can start using this information to ask questions like, how do these things interact with each other? Can I work out their multiplication table, perhaps? And in this way, we gradually piece together our understanding of the group that we're trying to study. So in this case, we did this one already, so we know this group quite well. This is Z mod 2 cross Z mod 2. And you can imagine, since I'm picking two things in order 4, that the other one will be different. So let's look at the other example I have in mind and try to see like what's different about it. That example is x to the 4 plus x to the third plus x squared plus x plus 1. And in some previous problem solving, we were interested in polynomials of this type. And so let's try to investigate. With this polynomial, we know that the thing that solves this is going to be a root of unity. What kind of root of unity is it? Well, in order to see, we remember that if I multiply this thing by 1 minus x over 1 minus x, doesn't do anything when I do, then, sorry, I should probably do that x minus 1, right? It makes the algebra a little bit simpler. Maybe it doesn't matter. I like this version. We can see that this becomes x to the 5 minus 1 over x minus 1. And so, therefore, this must be the minimal polynomial of a fifth root of unity, which we were denoting by omega 5. And one of the ways that I'd like to see this that's really elegant, that uses geometry, is to remember something about what I was saying with the exponential. If you know about complex numbers and polar coordinates, then you know that since omega 5 is e to the 2 pi I over 5, right? I have 1 here, and then this is cosine plus I sine with an angle of 2 pi over 5. So maybe it's like here. And then there's another one kind of over here, another one kind of over here, another one kind of over here. And my drawing skills are not very good, but they all have distance 1 from the origin, and they're all angles of 2 pi I over 5. So this should be a regular pentagon. It doesn't really look like a fully regular pentagon. So I'm just going to write should be a regular pentagon. And therefore, when you add these numbers up, they have to give 0 because it's symmetric. In particular, the sum is the same if I permute all the elements. So if I multiply everything by an omega 5. And what is the only number in the plane with the property that the sum, which I'll call z, is equal, sorry, I don't want to use zeta, we're using omega. Omega 5z, that's the same thing as saying omega 5 minus 1, z equals 0. Omega 5 is not 1, omega 5 is a complex number, therefore the sum is 0. So this is the minimal polynomial of omega 5 by geometry. Very cool. So now I know the root field of this thing, right? Since we talked about this object before, this is the root field Q adjoin omega 5. And so what are the automorphisms of this thing? Well, I know that I can send omega 5 to any of its other powers except for 1, right? If I send it to 1, then it's not injective anymore, right? Because 1 already goes to 1. So the 4 automorphisms that I have are determined by what power, which power, doesn't matter, of omega 5 I send it to. And so in that way, we can see that if I take, for example, the simplest one, how about I send omega 5, so I send 1 to 1, of course, and then I send omega 5 to omega 5 squared. That seems like a simple enough thing to do. Well, this, we could call this element sigma. What is sigma squared? Sigma squared still sends 1 to 1. Omega 5 is then going to be mapped to omega 5 to the 4th power. What about sigma cubed? That sends omega 5. Each of these guys goes to its own power. That's omega 5 to the 8, right? Because I have to apply to each of these guys again. But omega 5 has the property that omega 5 to the 5 is 1. So this is omega 5 cubed. And so we know that this group can't be different, right? Even if I didn't know, so I know I told you guys previously that the powers of omega form a cyclic group. First off, you'll notice that this is not like the same cyclic group on the nose, right? Like the ordering that we're seeing the things in is a little bit different. But moreover, I know that this is a group of order 4, but I found inside of it an element without order 2. Right? I mean, I could have declared that conclusion even just here. So even if I didn't want to calculate this, I would automatically know that sigma has order 4. And indeed it does, because sigma 4 takes omega 5 and sends it to omega 5 to the 6, which is equal to omega 5 to the 5 times omega 5, which is omega 5. So I knew this by abstract reasoning before I calculated anything. And in particular, I could see that the Galois group of Q adjoin omega 5 over Q was isomorphic to Z mod 4Z. All right, I think this has been a good example. I think this is a good length. There's quite a bit more I want to unpack about Galois groups. So I hope you enjoyed this nice little intercession. And we're going to continue in the next video probing more of the group theoretical properties of Galois groups. See you in a sec.